A 2D array is a data structure that organizes elements in a grid-like format with rows and columns. They are used in image processing, game development, scientific computing, and mathematical operations. There are multiple ways to create 2D arrays in Python. You can use nested lists, list comprehension, or the NumPy library. Here is an example of creating a matrix using nested lists. The matrix is assigned to a list of lists containing the numbers 1 through 9. Here is another way using list comprehension. The matrix is assigned to a list of lists. The inner list is created using 0 for j in range 3. The outer list is for I in range 3. The output is a 3 by 3 matrix containing zeros. NumPy provides efficient operations for matrix manipulation, including faster computation, memory efficiency, built-in matrix operations, and broadcasting capabilities. Here is an example using the NumPy library. First, we import NumPy as NP. To create a 3 by 3 matrix, we assign the np.array and pass in a list of lists that contain the numbers 1 through 9. To create matrices with specific values, we can assign a variable called zeros to the np.zeros method, passing in a tuple with 3, 3, that creates a 3 by 3 matrix of zeros. Similarly, a variable called ones can be assigned to the np.ones method, passing in a tuple with 3, 3 that creates a 3 by 3 matrix of ones. To access elements in 2D arrays, let us define a 3 by 3 matrix with values 1 through 9. To access individual elements, assign a variable called element to the matrix at index 1, 2, meaning row 1, column 2. Printing the element will output 6. To access an entire row, assign a variable called row to the matrix at index 0. Printing the row variable will output the first row 1, 2, 3. So in summary, to access an element in a 2D array, use the index of the row and column. Remember, the index starts at 0. To iterate through all elements in a 2D array, the matrix can be defined as a list of lists with values from 1 to 9. To loop through the matrix, a nested for loop can be used. The outer loop variable I in the range of the length of the matrix, and the inner loop variable j in the range of the length of the matrix at index I. Print the matrix at index I, j and add a space ind equals space. After the inner for loop, print a new line. The note to remember is that the outer loop iterates through rows, and the inner loop iterates through columns in each row. The output is 1, 2, 3 on the first line, 4, 5, 6 on the second line, and 7, 8, 9 on the third line. List comprehension can also be used. Simply write print the element and a space in the end for each row in the matrix for each element in the row. There are many matrix operations. For example, matrix addition is adding the corresponding elements. First, import NumPy as NP. Define the matrix A assigned to np.array, passing in a list of lists with values 1, 2, 3, 4. Similarly, define matrix B assigned to np.array, passing in a list of lists with values 5, 6, 7, 8. Assign C to A plus B, print C. The output is a list of lists with the first row containing 6, 8 and the second row containing 10, 12. Another operation is matrix multiplication, which is a dot product of rows and columns. The same code as above can be used, except C is assigned to np, with A and B as parameters. Alternatively, C can be assigned to A at B, which is the same operation. Printing C will output a list of lists, with the first row containing 19, 22 and the second row containing 43, 50. Some advanced matrix operations include transposition, determinant, and inverse. Transposition is where the rows and columns are swapped. To do this, first import NumPy as NP. A matrix can be defined with values 1, 2, 3 in the first row, and 4, 5, 6 in the second row. A variable called transpose can be assigned to matrix.T, which is the transpose. Printing transpose will output 1, 4 on the first row, 2, 5 on the second row, and 3, 6 on the third row. To calculate the determinant and inverse, import NumPy as NP. Define a matrix with values 4, 7 in the first row, and 2, 6 in the second row. A variable called det can be assigned to np.linealg.det, passing in the matrix. A formatted string can print the determinant to 1 decimal place. The determinant is 10.0. A variable called inv can be assigned to np.lineout.inv, passing in the matrix. Printing inv will output 0.6, negative 0.7 in the first row, and negative 0.2, 0.4 in the second row. Matrices are powerful tools for transforming coordinates in computer graphics, robotics, and physics simulations. Common transformations include rotation, scaling, translation using homogeneous coordinates, reflection, and shearing. These operations can be combined into a single transformation matrix, allowing for efficient computation. As an example, R can be assigned to a list of lists containing cosine theta, negative sine theta, and cosine theta. Common matrix algorithms include matrix search and spiral traversal. Matrix search involves efficient searching an assorted 2D array where elements increase from left to right, and elements increase from top to bottom. To search the matrix, a function called search matrix can be defined with parameters matrix and target. Start from the top right corner and get the number of rows and columns using the len method. Assign row to 0 and column to columns -1. While row is less than rows and column is greater or equal to 0, if the matrix at index row, column is the target, then return true. Otherwise, if the matrix at index row, column is greater than the target, then decrement the column by 1 to move left. Otherwise, increment the row by 1 to move down. If the target is not found, then return false. Spiral traversal involves traversing a matrix in spiral order. Start from the outer layer and move inward in a spiral pattern. To implement this algorithm, define a function called spiral order and pass in the matrix. The result can be stored in a list. If the matrix does not exist, then return the result. The top and bottom variables can be assigned to 0, and the length of the matrix -1. The left and right variables can be assigned to 0, and the length of the matrix at index 0 -1. While top is less than or equal to bottom and left is less than or equal to right, traverse right. For I in the range left to right +1, append the matrix at index top I to the result. Finally, increment top by 1, and continue with the other directions. 2D arrays have many practical applications including image processing, game development, and machine learning. Digital images are represented as 2D arrays of pixel values. Matrix operations enable filtering, transformations, and computer vision algorithms. Examples of image processing include image filters such as blur and sharpen, edge detection, and facial recognition. In game development, games use matrices for 2D and 3D transformations, collision detection, and implementing game mechanics like tile-based worlds. Examples include character movement, grid-based games, and pathfinding algorithms. In machine learning, many ML algorithms rely on matrix operations for data representation, feature extraction, and model training. Examples include neural networks, principal component analysis, and recommendation systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.